every week. The layout, button layout and behavior is different every week. I just like, what the hell you doing, YouTube? Fine. Coffee Compiler Club. Here today to talk about compilers and language runtimes. And I don't know, everything to do with things to do with home ownership versus what you do with your spare time. Hey, Arthur. We're all being recorded, show up
Oh,
on YouTube within hour, two, day, something. I normally have no set agenda. I have a brief one. I'm trying to get chapter 21 encodings put to bed. Um, and we found a last minute bug. Tommy's been working on it. Tommy's been a real champ here. He has piled in and done a ton of work on chapter 21. I don't have his real name. I have only his GitHub handle or his Discord handle or whatever. Um, bunch of PRs, or got his name on if you want to go find out more about the guy. He's done great work, great stuff. Other things, chapter 21 is the first time in three chapters that we can test. So 19 was instruction selection, 20 was register allocation, 21 is encodings. After we get encodings, we can actually run the code. And upon running the code, we found all kind of bugs. As a surprise, 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 here they are. And some of the bugs came from instruction selection, some came from the register allocator, and some came from the encodings, and they're all over the map. So there's a lot of this chapter has included a lot of fixes for prior chapters, and I think that's just how these things go. There's
how
a
easier is to spot the bugs in the register allocation and the instruction selection? So
sorry, say again. I mean,
how
fix.
easier is to spot bugs in obviously the output isn't what you expected, but
Yeah.
how do you
Well,
worry about that?
right. So you eyeball instruction selection, register allocation, but the old Mark One eyeball has limits on how well it can spot things, right?
Mm.
And then you eventually, run the thing and it crashes. Okay, now who's to blame, right? Where'd it come from?
Mm.
So the most recent code is encoding. So you suspect, oh, it's an encoding bug. And you go stare at the encodings and you get online disassemblers and you go read the miles of Intel docs and the 10,000 variations of how they do things. And you kind of sort of figure out it is or it isn't an encoding bug. There are plenty of those. You fix some of those. Then you get register allocation bugs where registers were being picked by the allocator that were not allowed. And so the encoding didn't assert on them. And instead, it just merely emitted crap code because of that.
How do you figure out that it's picked a register that it isn't supposed to pick?
Well, so we have these fancy prints. So you go to the assembler print,
Mhm.
which tries its best to print out some human readable version of assembly that's generically RISC-like across all architectures, and it's the same for them all, RISC and ARM and x86 and whoever else things. Um, I claim it's way the hell reader than any of the Intel AT&T
Mm.
assemblers. Fine, but it's also for cross-platform, so it does the same syntax for all the chips. And merely it says one thing, and you take the bits that were encoded and throw them in a disassembler, and you get a different thing.
Mm.
And so, it's not obvious. You get a mile and miles and miles of assembly where it went wrong. So you have to go to some amount of debugging and figure out where you went south and crashed or whatever.
So
And
by now you have how compared to approximation to compared to GCC compiled the same kind of function. What is
oh, you
the
mean like code quality?
yeah code quality? Yes.
There's a whole lot of tuning to be done. So there's no loop optimizations except loop invariant code motion.
Mm-hmm.
And then there's no tuning on instruction selection. So there's probably 10 to 15% instruction size reduction on an Intel by just picking better opcode layout formats or whatever. There's some stupid things in there for sure. Like I put aside all those kind of optimization tunings just to get to where it was functionally correct and running all the time.
Mm-hmm.
Um, and a lot of those can just be things that are small, focused updates, can be nitpicked your way along. Um, the lack of loop ops will hit sort of larger, longer running programs and the inlining is really lame, really
Mm.
lame.
Yeah, yeah.
And that's just like, time to do some performance work at some point.
Mm.
So the thing I'm going to do first is add strings, and we're just linking barely against calix. So strings and external linking for I/O, get some reasonable I/O infrastructure in place so the language is like usable. Um, and if people throw in optimizations along the way that are like, you've got a
Mm.
shift left followed by a shift right, can't we turn these into some sort of and mask or whatever? I saw that this morning, so I know it can
Mm.
be done.
Mm.
Something going on here. You could do something better than what's going
Mm.
on. Yeah, those are all nitpicky things. You pick them up one at a time. Great. So
Mm.
there's a lot of that kind of stuff missing. So it's not GCC 02 yet. Um,
Mm.
it's definitely well better than any of the debug setups that people do. And it doesn't have any debug info. So, it's for a part-time project that's got, a handful of people who pile in on a regular basis. I think it's doing
Mm.
pretty well. As a
Mm.
tutorial discussion on how to write a compiler, I think it's doing okay. I think the big learning I want to put out for the chapters here is that the 1920-21 last end of code gen pieces are hard to debug in isolation. You kind of need the end-to-end path. Like I ran an evaluator on CF nodes directly to go verify correctness
Mm.
up until instruction selection. And I could do an evaluator on the selected Intel instructions, and I would be testing my evaluators how well it matched what Intel instruction matched, but it wouldn't really be testing an x86. So then you get into, you need register allocator, which has its own giant pile of bugs. And some you can eyeball, and some you can test that you didn't break live ranges, but you kept the same semantic meaning. But some are just like, hey, you're not allowed to use RSI in this funny particular situation. So, you picked the wrong register.
Mm.
Fine.
Mm.
Um,
So small code, small functions definitely help to easier to spot the end product. So where things can might went wrong.
yeah, we
So
got a collection of small functions that are all running up until Linux on external libc calls. That was
mm.
last night's discovery. On Windows, I can compile Win64, the MS ABI calling libc, and it's great. On
Mm.
Windows, I can use the sys5 ABI to link against GCC emitted sys5 code, and that works great. But I'm
Mm.
still linking against Windows libc, and so the Windows call uses the Windows ABI for the malloc for allocation. Okay, that works.
Mm.
The Linux version of things on their sys5 calloc crashes with corrupted heap, which is almost surely the wrong ABI for calling calloc under sys5, but sys5 on Windows works fine.
Mm.
So like, okay.
Mm.
So that's where we're at right now. And yeah, that one goes down. We'll declare victory and walk away, and
Mm.
go on to get like strings. I think strings
Mm.
are important, but we should be able to link against C code, libc, and run.
Mm. Mm.
So
Mm.
it's getting there.
Cool. I expect more people to pick it up once it's fully functional, right? As
Yeah,
if.
you kind
Mm.
of need strings and I/O to do anything
Mhm.
reasonable.
Mm.
I've been dodging strings because I want to do them in the language instead of as a rare raw primitive. And I think
Mm.
I can do a really nice job with strings in the language. So
So
I want to
why
do,
why do you think you have more power when it's inside the language? What can you do
yeah.
better?
Well, so the first thing I'll do is I'm going to fold strings and arrays together. It's like the C array following a struct thing, but all the time.
Mm.
So that if you have a struct, you're allowed to have an array at the end. And if you have an array, you're allowed to have named fields in the front. And you just fuse those two together and it's the same thing. Okay. Then method calls are like, that one's already sorted out. Method calls will just be, I put a function in a final field and an object. Well, it's a final field, so it's not modified. There's no cheating it here, so I can move it off to a prototype. And now I have a method call syntax. I can just say, class string, and I want to have a string append, and append's too long a word. I want to have a string add, I want to have a length, and I want to have a char, and I want to have a da 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 da. Name your functions. You're gonna pile on your strings. And then at the end of the structure, you also have an array, which has a length, and you have a hash code as actual data fields. And then the array is embedded in with a string object. So the hash code and the length and the character data are all smushed in the same blob. They don't have to take a Java style indirection to get to the car array. And there's your string.
Hmm.
And then you can go add more features by writing simple code in the string class, and then you just add.
So there will be represented as UTF-8, 16,
No,
something.
so that's a different one. So there's a I want a classic UTF-8 string,
Hmm.
and then I want another string-like class that maybe says I'm a C string faker. Call it a CSTR or a ZSTR. I'm a zero terminated, whatever, hell. But I can be to and from passed around to libc without crashing and burning, just to make portability easier for everyone involved, right? But I won't call it a string. I'll call
Hmm.
it a C string, just like Python. Just like Python does it. Or a U string for a Unicode 16 or U16 string or something, right?
Hmm. Hmm.
Get the default string will look like what ASCII strings have looked like for umpteen years, except to be length checked instead of zero checked. And then hash code's really common on strings, so space for a hash code.
And interoperability between them will be
Oh,
via.
so any one
Hmm.
of the string classes can have arguments of the other kinds of class wherever you want to do interoperability.
Oh, okay. By methods, no hierarchy, no base string on C string, which extends
Oh, I
anything
don't
string
know. So I
here.
don't have
No.
any subclassing
Yeah,
yet.
yeah, yeah.
I tend to think about having single inheritance subclassing, in which case there may be a common base class and people extend from it. Yeah,
Mm-hmm. Mm-hmm.
that could happen. It's not there. Language
Mm-hmm.
design versus implementation. I designed too much and implemented too little. Here I am implementing first and adding design while I can still add design.
Mm-hmm.
And the
Cool.
goal remains to be a tutorial, not to be the be all language. But to the extent you can make a language that's useful, you get a hell of a lot more users and,
Mm-hmm.
and productivity out of it and understanding of how the interconnections go. And I think I want it to be usable. Fine.
Cool. Cool. Okay. Next
So yeah,
question. Next
strings
topic.
are
Mm.
next in my head,
Okay.
and remaining encoding bugs will get dribbled out as we go. So the RISC-V guy has got an emulator. And I know Derek, who's not on the call right now, is using it for his custom embedded RISC-V. So the RISC-V encodings have been beaten on a fair amount, and I think they're in reasonably good shape.
Mm.
And we have an ELF file comes out of everybody, and I'm pretty sure Derek's taking the ELF file and using it. So we're through an ELF file and several other simulators, two other simulators from Derek plus the one I have. And we may get a QEMU one going here at some point. So I think the R5 port's in good shape. x86 port was not because of
Mm.
various stupid encoding bugs, and then now whatever the calling convention variations. Other things we could do, calling conventions are all things you can turn on to a couple knobs. There's a few functions to implement a calling convention. So I'll probably add another calling convention, which will be the simple calling convention, which will basically not pin any registers or any calls and do global register allocation within a compilation unit.
Mm.
Um, but that live with libc convention of host platform or target platform. It's cross compiler, so target platform for cross calls.
So
um
it 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 will the register allocation for simple calling simple would be simpler. Mm.
it just you don't get pinned at registers, certain
Mm.
registers at call sites all the time,
Mm.
and your caller callee save is a lot more flexible. So the total amount of spill code involved for going a few layers of calls deep should be down.
Mm.
The standard
So
caller callee spill split is so that you have few spills at leaf calls, and leaf calls are the most common because they're the bottom of your execution tree. Okay, fine. And then giving the allocator some more freedom around those should let a few more layers go up without you having to spill things. And presumably you get better allocations when viewed more globally.
mm. Mm.
And that's another performance hack. It's small relative to any hot loop when you lack loop optimization. So that one may or may not happen right away. I'm geared to make it easy to do, but loop optimizations are still going to be, king for raw performance on benchmarks.
Yeah.
So kind of the longer term goal, once strings and IO are looking good, is to go pick up like what's the Rosetta Stone, the code Rosetta Stone examples, and or the Debian language shootout kind of things, and go code a bunch of those things up and see that they work.
Cool. Cool.
Hmm. What
Yeah.
All right.
else?
Yeah. Yeah.
Uh,
Alan?
yeah, so I had a question. So let's see. So we were discussing AA versus simple. And so you said like, AA, you sort of leaned into this kind of theory side, and then simple, you kind of leaned into the implementation. Um, and so like for me, I just certainly I wouldn't say I've done any implementation. I just, it's all theory so far. Um,
There's a
and so
usefulness to doing some implementation for a while because of the amount of you learn what's reality or what's practical and what's not.
yeah, and so there's certainly a question of where to start, and I'll leave that for a different day. But like the question I had was like, so for example, I'm very interested in the unison register allocator, and so like, that does have an implementation. They like kind of got something working for LLVM, and he was on here like a year ago, and we talked to him, and I mean, he didn't come out and say that the code was bad, but like he basically said, it wasn't merged into LLVM for a reason. Um, and so, so I got the impression certainly that, at least to understand what the code was doing, I'd have to write like basically a new version of it. And so I was wondering, like, would you start with writing a register allocator, or would you start with like reading the papers and understanding the theory, or like where would you go in terms of the
Ah,
implementation versus theory side
it,
of that?
yeah, if your goal is to do register allocation, but what is that your goal?
Well, the goal is to do like the optimal register allocation that Unison does. And so
I
that's
see.
like,
I
yeah.
would I would pick the easiest, most well-documented register allocator you can find, which would be some variant of linear scan. And I know there are people on CCC who've been playing with Ian Rogers' version, which is a fairly modern, recent, and I think he did a fine job with documenting, and there's talks about it. Go implement not Unison, some other easier register allocator, just to see all the issues and understand what people are talking about, and kind of figure out what the actual story is on these things. The graph curling one in simple is not so simple as I believe Eon's is, but it's also well documented. After that, I don't know many well documented ones, but you want to hands on yourself. You want to do one yourself because then you suffer all the bugs that you write and you figure out what's hard to do about these things. Like there's a pattern and a technology and a technique to debugging register allocator bugs. And some of that's got to be done by learning by doing. So it's not the actual writing of the register allocator, it's actually debugging the allocator you wrote. So start with a simple allocator and figure out, when it goes wrong, what does it look like when it goes wrong? How do you tell that it's wrong? So on.
Thank you.
Yeah, yeah. Andy, did you want to say something? You're like rare guest here.
I don't know. I've been working on escape analysis,
Well, there you go. That's a good topic.
and been trying to figure out the extent to which I need to combine escape analysis and points to analysis, because in our language you can take the addresses of things and pass them all around, and so you quickly kind of lose track of what can refer to what.
Yeah.
Which
What is our language?
.NET.
.NET. Okay. Not C# specifically or F# or something.
Well, I mean, C# turns into what we compile, right? Just like in Java, there's many source languages and one IL.
Yeah. Yeah. Yeah, yeah.
So anyway, so I've been wrestling with that, and then also looks like I can prove that a lot of things don't escape that could go on the stack, but they're big, and so I'm like, well, what do I do with these things?
So I wrestled a long time with stack-based allocation at Azul and included escape detection, which meant I didn't have to prove, but I could discover practically that this thing doesn't actually escape in the running lifetime of the program. And there are plenty of big things.
Yeah,
And now what do you do with the big things?
yep, yep.
So you go first.
I don't know. We're just wrestling with that, and then how all of this meshes with our async implementation, which likes to suspend method execution in the middle and like hoover everything off somewhere. Like if I start putting tons of state onto the stack, they're going to be like, "What are you doing?" I have to copy all this crap. It's like, okay,
Yeah,
honestly.
I see. So I did a first version, put everything actually literally on the stack, and it just ran out of space. So I had a size cut off and I gave up, but then I couldn't, and everything you gave up on was always big array. And the big
Yeah.
array had a million pointers, and then you lost them all to the heap if you put the big array on the heap. So then I went to a side stack that had to be in the heap space because it was too big.
Mhm.
But then I lost my cheap escape detection test. So then I went to a side stack that was not on the general heap, and that was working okay, except that for a large side stacks of things that were very static, I really wanted a generational collector anyhow. Like the stack collector was fast and easy because it didn't have any coherency issues. It was all self-local, and most of the bottom frames are all hot in your cache anyhow. And so he
Yeah.
self-crawled his GC. That's the great part. The downside was when I had all this old stuff that was thread local and large, I really wanted it still be walked by the existing collector
Mhm.
because he was parallel, incremental, concurrent, background, every possible thing. And I just didn't, I couldn't compete against that in my one thread.
Right.
And I didn't want to write a thread local variant there of it. And of course, it wasn't set to say, and here's my heap, and here is a separate private heap that none of these pointers cross. So that wasn't available. So it's kind of a bitch.
Yeah. Yeah, I think
Question, Andy?
I'm kind of in the same camp where our GC technology is like siloed off and it's like, very specialized. And so it's not easy for me to go in and be like, hey, like I want something that's kind of like what you do, but just a little bit different. It's like,
Mhm.
Can you guys hear me?
yeah.
Cool.
Yes.
Andy, it sounded like earlier you were saying you had to copy stuff in and off do you do continuations now in .NET? Like rewriting the stack continuations, or is that something else?
We often have trouble rewriting the stack because part stack addresses can get captured into our live state. So we got to be really careful. Like I did OSR, and OSR ended up being painful because I couldn't just like take all the live state and copy it somewhere and then bring it back. I had to like either ensure that everything ended up in the same slot on the stack that it was before, or what I ended up doing is just leaving that stack frame hanging around and just referring to it.
So do you do something like do you have something like continuation support, like what Java built for the virtual threads?
It's not quite the same, but it's kind of similar. A lot of it used to be done at the language level. And we're looking to move a lot of it into the runtime itself.
Okay, interesting. I haven't kept up, so
yeah, if you look at .NET, there's this thing that we call async 2, which is like a reinvigoration of some of the async machinery. But yeah, so anyways, so we'll see. So there's a lot of stuff sort of going on where I always get kind of leery when I get to the point where I can see there's a bunch of possibilities, but I'm just not sure like how much work it's going to be to actually make it pay off. There's only so many hours in the day and so many things you can work on. So I hate to like give up on something prematurely because I just don't understand how to do it. But at the same time, if I can't figure out how to do it, it's just going to end up being a waste of time. So anyways.
So you say your GC is siloed off. Is that team like approachable? Can you go talk to them and say?
Somewhat. I don't know how. I think that's one of the things I need to do is basically make a pitch to them, like, hey, let's go do this thing as an experiment. So we've gotten better at being able to do experiments, so that's good. like people realize maybe it's worth spending a month working on this thing and it doesn't pan out. That's okay. Like, so.
I burned more like 4 months on stack-based.
Whatever the amount of time is, some amount of
right.
time.
Yeah.
So, but, it's always competing against all the other things they're trying to do. So they've been thinking about trying to do like a low latency GC with read barriers and all of that fun stuff, which we don't have. So.
Yeah, read barriers were a pain to put in, but they paid off.
Yeah.
A bunch of things were a pain to put in and paid off, but you had to decide you're going to do it. Yeah.
Yeah, we also haven't, I don't know if people have even paid attention to .NET at all, but we had an interesting project go on for many years called Midori.
Mm-hmm.
That was an operating system all built out of basically C#, with very little native code anywhere in the system, and we did a lot of innovative things there. So we had a special GC for kernel mode that used read barriers and was kind of real time, very minimal pause, but. So there's been some work done. It's just it was in a completely different world and a completely different code base and by a completely different set of people. So
didn't make it into the mainstream.
No.
Other than blog articles, the blog articles made it into the mainstream.
Yeah, I read the blog articles.
Yeah, Joe Duffy wrote a bunch of stuff. I don't know. You can probably.
He's a good writer.
So, and then some of those things have made it back into main.NET. Like span has been kind of one of our big innovations. So. Kind of
I'm sorry, what was that?
We have this type called span of T, which just represents a range of memory. It could be heap memory, it could be stack memory, it could be any kind of memory. And so we've gotten away from patterns that do a lot of allocation in order to kind of chop up memory ranges into things. Like if you were asking for like a substring of a string, you wouldn't necessarily have to like go actually allocate a whole new thing and like copy the bytes over. You could kind of point at the middle of an existing string and be like, I have this chunk of you. That was something that was in Midori that was pretty popular. So that's kind of
lifetime management on those.
Yeah, these particular types are restricted to only being on the stack. I don't know. We've had some discussions like we allow you to point into the middle of objects. I think like in Java, if I remember right, you can't really have just like a raw pointer into the middle of an object, right? You got to like
disallow because
base
the GC
plus offset or something like that. But we allow it, but we only allow them on the stack. But there's been some discussion: should we like allow them everywhere?
C2 gets away with a pointer to the middle of an array, but I had to put in the special hack for the GC folks myself that had a GC pointy unwinds the middle pointer to a base and offset and then rewinds it back. I can have derived. Called derived.
We had that because we always want to like point below the start of an object for a while. Like, don't worry about it. We'll eventually like pop it back into the object, but we can't allow it. So speaking of weird cogen bugs, when you reassociate some add tree and inadvertently point below an object for a little while, and you're just unlucky, and the GC kicks in right there. It's like, what is this? And it blows up, and you're like, oh.
Safe points. You don't have those at safe points.
Anyway, so that's some of the
derived
stuff.
Pointer.
Yeah,
you do the hack. Yeah, just for the safe point, you do the hack.
Yeah.
All manner of very low frequency bugs that have to be fixed.
So I have a question. So about so Midori, like, I don't know. I mean, I guess one of the emphasis in Midori was on concurrency.
Yeah.
And so like, I don't know. It sounds like you work on garbage collectors a lot. So I was just wondering if you had like any sort of advice for people implementing garbage collectors on concurrency and memory management, like mistakes not to make.
I don't actually work on garbage collectors.
Oh, okay. Sorry.
They're like, I wouldn't say they're the bane of my existence, but we spend a lot of time just trying to make sure the garbage collector continues to be happy. Because it has this particular worldview that you have to conform to.
So you use garbage collectors, but you don't write.
So when in our system, and I think this is probably true of a lot of systems, the the soundness of garbage collection relies on the code generator, like giving it information, right? We call this, and if that information is wrong, well, then the garbage collector will do something bad, right? And eventually the program will crash and
Right. It's very
users will
fragile and
be
it's very
angry.
hard to catch the memory bugs, I'd
Yeah.
say.
Yeah. So we do a bunch of stuff to try to surface these things, like we were talking about. From the standpoint of the code generator, GCs effectively almost never happen, right? Like every, I don't know, 10 million instructions, you suddenly get interrupted somewhere and GC happens. And so it's very easy to have bugs that just sort of lie in your code forever because you just never had a GC at the wrong time. So we have a thing we call GC stress that basically initiates GC at every possible point where GC could be allowed. And so that's great, but it takes forever, right? Because like GC is slow. And so instead of it doing one every 10 million instructions, if you do it every, 10 instructions or whatever, suddenly things run glacially. So it'll catch some bug, which is great, but it's not like a guarantee. And then, the worst of all is the intersection of GC and EH. Like if you have in the middle of doing some exception thing and suddenly GC kicks in, well, now exceptions are super rare. GC is super rare. Now you have like super rare squared. So the bugs there tend to be like the hardest ones to find, because how do you force exceptions to happen a lot? Well, you can try to play games, but that's something that's a little bit easier, a bit more difficult to kind of inflate the rate.
Okay, so the model I'm thinking of is kind of like you have a continuous GC. So it sounds kind of like you have this GC stress, but it's always on.
Yeah.
And so I'm just wondering, like, are there any bugs that are hard to catch even with GC stress turned on? Like, is that,
Yeah, well, like, let's say I failed to report a GC pointer to the GC in my information, right? And a GC happens. If the GC doesn't actually move that object, nobody knows, right? Everything still works, right? Oh, you got lucky. So one of the things I try to get our GC people to do is like, I want you to create a mode where every time you GC, you move every single object and you make all the memory that those objects used to be on be inaccessible. So that if I try to do anything with that old GC pointer that didn't get updated, program blows up right there. And I'm like, oh, and I catch it very close to where I screwed up, right? I'm like, no, we can't do that because we have pinned objects that can't be moved. Like, okay, well, what about the ones that can be moved? So we still have this dialogue back and forth. We haven't ever built this thing. I think it would be super useful. But you have to think about like, for these things which are hard to catch, like what is your strategy going to be for like trying to flush them out? Because eventually your customers will find them. And usually you don't want to be in that situation because it's always like some big, gnarly, important customer and, business people are getting angry and talking about money and you're like, ah.
Okay, so I've read
you're in business anyways. Yeah.
So there's like some literature about like one is called the diehard allocator, and so like this diehard allocator, like it really does a lot of randomization and stuff, and it just makes it very easy to catch these sorts of bugs. So and so it sounds like what you're saying is that's actually very important when you're designing the memory system, is to make sure it supports this kind of hardening and randomization and stuff.
You're going to have bugs, so it's worth planning ahead. Like, what are you going to do when things aren't right, and how are you going to catch it? We often forget these things. Like one of the things we do is we pretty aggressively dog food our own builds, and so it ends up that often the first torture test for like new things is building yourself, and people usually don't think of a build as a test, so we don't have the same infrastructure for capturing errors during a build that we would if we thought we were running a test. And so like, hey, the build broke, and we're like, well, okay, you were doing like 10 million things and something went wrong. Like, how do I recreate it? And they're like, well, you have to run the build again from the beginning. I'm like, So anyway,
I was actually just today.
Yeah.
Sorry. Just earlier today, I was knee deep in a GC bug. I'm trying to turn my currently not interleaved garbage collector to be interleaved, and I ran into these exact problems. Like, I have a bug somewhere, but where is it? Something odd happens, and I can't figure out what it actually is, so I can't even start properly debugging. And one of the things that I kind of started thinking, like nothing new, but because I happen to be using tagged indexes. So I'm not using actual pointers to the garbage collectible data, but a tag and an index. I have 3 bytes there left over. And I figured maybe I would want to do, at least for like debug builds or testing builds, I would want to put a like a liveness index into that 3 bytes that just keeps going in circles.
Yeah,
and every time I deref, I check, does it match the one on the heap?
Yeah. So Hotspot has a series of tests are all called blah, blah, blah a lot, including GC a lot and SafePoint a lot and dopt a lot, and every other kind of thing. And most of them also have a span on them. So you can say, don't GC at every point because it's too slow, but GC every 1,000 points or GC every n points or whatever the thing is, or pseudo random distribution that you can repeat kind of thing. And the tester guys go crazy with those when they have cycles. But that's one of the ways to get that.
Right.
And we did do the thing that we had a mode that said, and fucking move everything. And there was even a version of that did, at least in the old school parallel GC, when we were first bringing it up, we did a mode that said, move everybody and then protect the heap. So the heap flip-flop between 2 different heap spaces every cycle. So that leftover pointers that got chased would get bonked right away. Yeah.
Yeah. I mean, I guess all I would say is just plan on there being bugs and, think about how you're gonna find them.
It's a fast path, slow path optimization. The fast path says things are good. I'm going to take shortcuts and go quick, and you have to have it. And then that means the slow path is also the rare path, and it never gets tested. And that's where all your bugs lurk. You got to figure out a way to have the slow path get correctly tested as well. Part and parcel of that job.
Actually,
what are you drinking there?
regarding
About
the Lagavulin whiskey, 16-year-old.
Oh, whiskey. Jeez, it's too early in the morning. Sorry.
It's 5 o'clock somewhere.
Yeah, 5 o'clock somewhere. Yeah.
It's always, yeah. I actually had a comment on the like leaving pointers around and so on. That's one of the things that I'm kind of very enthusiastic about what I'm personally doing, but just in general, I guess, as well. Rust's borrow checker is everybody's enemy or beloved on the internet. But one of the things that I think, or I'm kind of personally using it for, is if you abuse it enough, you can actually make it also check garbage collectible stuff. Essentially, like make sure you're not leaving garbage collectible pointers around when garbage collection could be happening. As long as you have actual save points that can be expressed somehow to the borrow checker, then you can actually get those guarantees. And currently it doesn't work really well. Like the borrow checker doesn't exactly like it, so you need to kind of hit it a lot to make it work. But I'm hoping maybe in Rust someday, or maybe in another language with a borrow checker, there could be the means to actually express this at build time without all that hitting on the head. And that would be like a very powerful thing.
It's the compiler to check that garbage collectible pointers, when they span a garbage collection point, got retouched somehow by the language spec. Because these are all like below the implementation. Like you can't do this at Java level because you can't see those pointers. So you look at the compiler IR level, and the question was, did it pass through? If it passed through safe point, so Java at least didn't GC at every point. It was only at safe points. But you didn't carry a value past the safe point that didn't pass through the safe point and get subject to rewriting.
Yeah.
There was a lot of hanging on leftover pointery things that could happen in and around, well, exceptions, as Andy said, definitely. Function returns occasionally. Yeah.
Yeah, it's interesting because it's a use of the type system and the compilers checks to try to predict bad runtime behavior. And I'd be curious, Matt, if you've seen any papers on that topic, because that would be an actual decent use of all these various provers out there and whatnot, all the investment being made on the compile time side.
So once the initial round of bugs were beaten down, the hangers-on that went for years were always in the transitions, let's say the exceptions, the transitions between compiled code and the runtime. Like you're flipping from a compiled to an interpreted frame, so you're de-optimizing. And somewhere in the de-opt, you allocated some RAM to copy the stack over and copy it back. And for whatever reason, somebody took a GC, was able to take a GC in that process. And the GC wanted to move things that were on the compiled stack, and some were copied into the side space, and then they were copied back onto the compiled stack. We had similar operations with Windows and windowing hardware, like half the machine's hotspot was ported to in that era had windowing hardware, all different. And the windows would be lazily kept on the chip and not spilled in all conditions. And then the GC would go rewrite them. And that was especially common around exception paths. Ugly stuff. I'm trying to think of what you would do with a compiler to go verify, with a language typing verify the transitions between compiled code and basically handwritten assembly, getting you in and out of the compiled frame and back to C code. It's a different compiled frame.
There was that like statically verified JIT compiler, or a paper on that published in November, or preprint, I guess, in November.
Heard about this.
Which would, I think it was linked into the Coffee Compiler Club chat at some point.
Yeah, okay.
But yeah, that would be useful in the transitions, I guess, like, because then you could have of course, the handwritten code could be written in a way that it is actually making sure that you check check all the stuff.
You're not
and now your JIT side.
But you're not handwriting assembly anymore. You're handwriting some type of language level
like,
thingy.
Yeah, like the basically entry into the JITted code would be, of course, there's some part, the interpreter part will be at least partially written by hand. And then when you enter the JIT code, now you would be in the realm of the formally verified JIT compiler, which is then making sure that, all the transition requirements are met on both sides.
Did you see Matt's link?
I did. I was going to make sure it was in CCC, and it did. So I haven't actually looked at it. There's coming in simple yet is what to do about memory management. Right now I have the epsilon collector. I allow you to alloc until you die. There is no free. So that has to be sorted out. And I'm torn between a GC language and, like a Rust style, like no GC required for people doing high performance or kernel-like things. And they want to be, able to not require a GC to do things. So there's some theory that there's a easier syntax to get the borrow checker to work or something. I don't know what. I'm fantasizing what the hell to do here. But yes, after strings and IO, probably something to do with memory management comes around. And I don't know what that's going to be.
Oh yeah, for strings, I just wanted to mention like Swift, because they have like a very, I don't know, I wouldn't say it's the best string API, but it's like relatively simple because they just say a string is an array. So
I'm trying to say a string is an array, and it has methods on it, but I'm really going to say it's all arrays are allowed to have any count of methods on them, and a string array is just an all array.
Yeah.
I think
and also, so okay, this is completely unrelated, but so for assembly, right? There's actually like some typed assembly languages. Like you can literally like go down to the machine code and like assign a type system. I think it might be a little bit too low level. Like me personally, I would like, use it before register allocation because it's just like, like hard coding registers is just you do have this aspect where um you have to like hard code the registers to certain things, and that doesn't really encode well in a type system. But
It should be unrelated. So certainly C2 and simple maintain the strong, I always expect many compilers to maintain the strong high level types all the way through to the machine code at the end. So at any given line of emitted machine code in any of the current simple examples, I can tell you strongly what type of pointer is and what this kind of this is an integer index or whatever the hell thing going on. The typing's preserved. Now, it's not a typed assembly that you can write any amount of assembly, but if you were to inject IR, we could verify that the types, we don't currently, but we could verify the types that you inject. In fact, if I was to let you to write a hand roll assembly, you're going to inject some assembly right into the C code or simple code, just like GNU, GCC, inline assembly, whatever. I would totally do type checking on those injected instructions.
well, the issue is that to have the types mean something, you need to start from like a higher level language. And so if and so the question is what that higher level language is, and that's sort of what I was talking about. And so like if your higher level language has registers in it, then it's like, I mean, a register doesn't have like whether it's an address or a pointer or an integer or whatever. So,
You sound like Forth now. Yeah, Forth is just untyped, and you have essentially got registers.
yeah.
But to be fair, a number of the languages we still use today are untyped with pretend typing on top of them. So
Okay, fine. As soon as you can do a cast of anything to anything, yeah, you're untyped. Right.
Oh, yeah. So you said you're implementing casts. So what is the plan for casts? Is it going to
Oh,
be
I'm
anything?
sorry. When you say implementing casts, right now I have casts internal, not at the simple language level, internally, that are used to uplift a value, a type after a test. So you do an is a check or a null pointer check. After the check, I know something more about the top value. That internally, that's represented as a cast node, and it turns into a join instead of a meet in the lattice.
Hmm. So, okay, so you don't have like coercions yet, where it's like I have this value of a type and I want it to be a different type or something.
I can convert int to float in the usual way where you do the mathematical IEEE conversion. I will surely have an int to float converter that says, give me the pile of raw bits, but those don't have any type safety issues. It's just piles of raw bits. There is I can't forge an int to a pointer. I cannot forge one kind of pointer to an incompatible other kind. There is a question of whether it's productive or safe to take a pointer and cast it to an int, like excluding moving GCs, casting a pointer to an int is done by hash codes everywhere. So C languages that are not expecting moving GC and they need a hash code, well, they take the pointer and they cast as an int. Of course, now you have an int, which is related directly to the pointer, and that's kind of a security issue. So, what you gonna do? But yeah, I don't have any forging of fake types of any kind. Simple is intended to be a safe language. Actually,
So
can't fake a final field either.
So you don't intend to allow casting a pointer to an int then? You're going to do like something else?
I haven't decided. So in the realm of things that need a hash code, they generally want to store it for efficiency, and they immediately have a hash function and a field. And what's the amount of extra work to say, go compute a hash like sensibly by staring at your object, as opposed to taking your base address and hashing it. And then the flip side of that one, or the piece of that puzzle, is to say, if I have a moving collector and you do the hash thing, you have to do the Java thing where you save the hash in the header. You have to save the hash somewhere because the collector moved the pointer and the hash is no longer valid, cannot be derived from the pointer anymore. So it's like, do I really want to have pointer to int conversion? What's the use case? Maybe, but it's kind of weak, so it hasn't happened yet. It might not happen. I don't know.
Okay. Well, I can say what Strausscut is planned to do. It's not implemented yet because nothing is. But So for Strauss-Cut, the plan is you answer it both ways. You say, yes, so if I want to cast a pointer to an integer, then I have this thing called a pointer, and it's basically an integer disguise, and it's a memory address. And then if I don't want to cast an integer to a pointer, then I have references, and that has this kind of opaque type, but it does have a stable hash code. So, yeah.
Okay.
And so, yeah. And
I've
so
al-
then, like, sorry, go ahead.
Well, I've also seen language so that Elm will take untyped from JavaScript into Elm, but he will do the cast requires a complete safety check on the thing that's being cast recursively deep to basically inject it. He does a full, it's type correct within the reachable bounds of whatever you cast it to. As another way to say, oh, you can hide it as a pointer and hand it to C code, and C code hands it back to you. You went to memcached and it came back as a pointer to a thing, and you verified by reading the progressively things through. Oh, okay, it still looks good. I don't know, maybe.
Well, the issue there is just that, like, verifying that something is the right structure and so on is expensive. And so you
Yeah.
don't want to pay for that. You just, you just want to say it's unchecked, it happens, and then, if it's wrong, it's your fault.
Well, them's your problems or whatever. There's your every C 0-day exploit starts from something along those lines. I sent you a packet of size 1001 instead of 1000, and you didn't bother to check, and I overwrote the end. And oh, if I do it enough times, I tickled your stack pointer somewhere, and never mind, you're off and return address injection or whatever else thing happened here.
Well,
Something bad happens, TM.
Yeah, I don't know, but like if you're handwriting assembly code, like how do you check that you're dealing with the memory the right way? You just look at it and you're like,
Oh, it's
basically.
right. Same as unsafe in Java and Rust. You wrote unsafe. Everyone stares at this code really hard. Did you break other invariants besides the obvious type level language invariants, like the GC didn't move this pointer, it was valid at one time, it is no longer valid, can you tell? It got moved to be valid for some other object that's unrelated to anything else on the planet that's not what it's supposed to be, and now you've punned two different pointers or something like that. That was one of my fun hacks that I filed a bug with Sun with about punning type strings. I could pun strings to different strings and override the strings with class loaders and then cheat on strings. And I filed a bug at Sun and I left. And a decade later, I got, hey, Cliff, we found this bug in the bug depot, whatever. Is this still a thing? And I'm like, well, let me go read the bug report. Oh, I put a test case in just for this case. I'll go run my test case. Look, I can crash your VM. I can inject and get inside anything, every Java VM ever, by rewriting any string to anything I want. And if you ran this test case, you would see that too. Okay. I think they eventually fixed it. I think I saw the fix go by. I think I also saw the fix being overly complicated, and I never chased it further, but I'm like, was not necessary to do this other thing. I'm kind of curious now if you actually closed the bug or you just made another epicycle, and I just had to go one more epicycle deep to get into it.
So the question is like, is simple, susceptible to this bug or not?
Oh, not this one. No. This was an overlap for like class loaders. It was a security domain, class loader, and class triplet. And you could compile two different guys with two different class loaders, rename the files on disk, and the loader, the JVM when loading would pun them together and declare them the same class somehow. I got them to let it slide by, but they were using different loaders. And so one of the loaders was a string thing that was not a string, not a Java string. And it opened a backdoor that let me edit the string basically. And you make an array of one of them and you would pass it off to this function, would fill it with the other kind of string, and you came back and you had an array that behaved and looked like a Java string, except I kept off the ability to edit any of your strings post-construction. And so you would, I went as far as saying, okay, I'm going to take a security domain thing and it needs to have this special passwordy thing, and I could edit the password the required whatever expected password. I could edit to anything I wanted. And then I wrote it out in a bug report, filed it, and said, I got other things. This is a runtime bug. It manifested itself as a compiler bug because the compiler, the C2, got it right and said, these two things are not the same thing because they fail the triplet test. And since they're not the same thing, I'm going to claim that one of them is rare and I'm going to deopt. And then we got this endless deopt loop because somebody somewhere was tickling this bug. And I had to go diagnose it. Now that I've said that, I haven't even thought about this in 20 years. I wonder if somebody else spotted it first. And if you ran it hot enough, C2 would blow up and not compile, and then it would get hot again and again not compile. And you got this endless deopt recompile loop. And I got handed an endless deopt recompile loop. But that turned into, no, this is like you handed me mismatched class files. The class file contents didn't match the bits inside, and it was cheating on strings. And then I was like, wait a minute, I can drive a truck through this hole.
So
Fine.
it's the security model was wrong. It wasn't your problem.
Right, right. Well, my problem was I needed to recognize that this code was never going to compile sensibly and to not try anymore and just say, it's not going to deopt, it's just going to run in the interpreter, go away. And let the interpreter do it the slow runtime way, and the runtime can decide to be broken or not. That was not my bug. That's why I filed it. I handed it off to the East Coast. It was West Coast, handed the bug to the East Coast. 10 years later, after I left Sun, 10 years after I left Sun, I got the bug question. Hey, is this still a bug? Did you try the bug report? Fine. Like I said, at least they made an effort to fix it eventually.
Stepping back a couple of steps regarding moving GCs and hashing pointers, in this case, I'm actually doing a crazy, absolutely crazy, stupid thing currently in my JavaScript engine, where like my GC is aggressively compacting or moving all vectors, or everything is stored in vectors, and they keep constantly shuffled downwards as stuff dies from in front. But then JavaScript has stuff like maps and weak maps, which are basically hash maps from object or possibly object to value. And for like primitive values, I generally can, or those I will hash with the actual data, like strings will actually hash with their string value. But then objects, I just go and rewrite them in the hash map on every GC currently. Like I will pick them out of the hash map and put them back in.
You'll rehash them.
I rehash them, which I expect will eventually become absolutely bonkers insane. But for now, when it's still trying out, it has been totally fine. Not a lot of big hash maps around, but I expect it will be a problem in the end.
But say, isn't every possible thing in JavaScript a hash map? I thought all objects were basically hash maps.
Well, the spec kind of says
that's Python.
Yeah, the spec doesn't actually say anything about how an object should be set up. So my opinion is currently that they are not hash maps. They're like basically just vector lookup tables. So I'm not rehashing every object on yeah.
But everybody who has the standard normal hash code and is a key in a table is getting rewritten on every GC cycle. You have some way to say that this guy was using his standard address of hash code. Okay. Interesting.
Yeah.
Interesting. Yeah.
I'm looking forward to if it's going to work. I think it won't eventually.
Yeah. But I guess I don't know. My thesis on that one was most objects don't need hash codes. And when they do, you know it. And so you'll just go put a field for the hash code in the object. That's part of the price. Same for locks in Java. Most objects never lock. if you're going to lock something, you're going to put a field that says, I'm a lock. Don't make everybody pay for the common case that you're not being used. Yeah, that's not getting used. Fine.
How do you decide the hash code though? At least like in a JavaScript case, my thinking here is it like people will actually put like objects, normal JavaScript objects as keys of a map.
Yeah.
But that object can change. You can add properties,
Right.
you can take away properties.
Right.
So
an identity hash code on this object. So you default
Yeah,
to
but-
making the user pick it, and then it's not your problem. That was my solution. The Java solution says there is a system native hash code, and he does a thing which used to be address based and now is a little more intelligent, a little harder to break. But we don't have the problem of the fields that define your hashable thing come and go and come and go. If that happens, like JavaScript, it's like the identity of the object. You have to have an identity thing in that object. Like, how do you know the object's the same when you throw a hashes? You're only doing an identity check when these kind of maps happen. You're only doing an identity check. You're not saying like global value numbering, common sub-expression relation is a hash, but I'm looking for structure. These two structures are the same. You're not. You're looking for identity. This pointer, and nothing else matters. Yeah. Well, don't move it. Don't change the pointer or rewrite everything every go. That's kind of ugly.
I guess one option, of course, would be to, especially since I will eventually be storing stuff in, I actually already do store stuff in like parallel arrays or parallel vectors, and some of that stuff will be itself. Well, wait, no, this ain't gonna work. Okay, so some of that stuff is in sparse side vectors, side tables, which are then themselves hash tables or maybe B trees or something like that.
Yeah.
So now, like if somebody has decided to use this particular item as a key in a hash map, now you would create a hash from some value, somehow calculate or randomize a hash value for this particular item, put it into a side table because it's rare that these will have a hash value, and now you reuse that. So you don't need to rehash the hash map where this is being used as a key, but now you have the side table, so you need to actually be rehashing that.
Right.
So
yeah, I'm still in the zone of the correct answer is the user declares he wants a hash code, and then he tells you what it is, and it's his problem to get it right. And if he's yanking his fields out from under his hash code is changing on the fly, and that's his bug. Okay, fine.
So I'll share my solution, which objects don't have identity; they're just data. So like you take like their in-memory representation, and like that's like a serialized as some bytes, and I mean you have to do a little bit of stuff like with big endian versus little endian and that kind of thing to make it like portable.
And pointers.
But well, pointers, yeah, so pointers they don't exist. What you have are references. And so references, they're nothing but identity. So like they have like a unique value that's
in
like
memory
their
you don't
hash.
have pointers? You only have references in memory?
Well, you have pointers, but they're so low level that nobody uses them.
But
So
You just said
you two
you're
need to
using
agree on it.
serialized form, which is pointers.
well, yeah, when you serialize a pointer, you have an integer, which is the memory address. And like, that's so unportable that nobody would use it. So they don't exist. Um, yeah. So, but references, they just have an identity and it's like a unique number or whatever. And that's the hash code and everything else you need to know about the reference. So yeah.
But
And so
when you store more data with a reference than just it's an identity.
well, no, like the only thing you can do with a reference is dereference it and compare it for equality and hash code and stuff. So,
Okay. Like if I need a unique thing in the land of Java or C, I'll allocate an object. Because I've allocated, that thing will never be equal to any other thing, as long as I don't let it be out for free or anything. And then I declare it a tombstone or a sentinel or whatever, and I throw it in a global and I use it in my algorithms for whatever reason. But it's a unique identifiable thing. And because it never dies, the GC never rewrites it except everywhere all simultaneously, the usual GC rules.
Right. And so in Strauss-Cut, you'd use a reference to the unit type. And so because it's the unit type, you know exactly what its value is. It's the unit.
Well, that's what I was asking. Reference has other data.
Yeah.
That's
well, I mean, it has data in the sense that it's the unit type, but it's also like the unit type contains no information. There's only one value.
Do your references point to have a way to access a pile of other data?
Yes, but it's side effectful. And so if you're writing pure code, you can't dereference a reference. And so there's like a very, sharp boundary between effects and pure code. And so you get that sort of restriction that like, as soon as you dereference a reference, you're in this imperative model of programming. And like you've already, you sort of, you've like, opened the can of worms. So,
well,
but when you serialize, it's pure. And so that's why when you serialize, your reference is just a value. So
okay, but then you have this mostly would be you expect to program in a serial in a pointer in a pure model with no side effects. So everything's like a closure, everything's just a new allocation of a new thing, and performance tied up with doing things with persistent data structures or whatever.
Right. Well, I mean, you can use references and you can have the imperative data structure, but then like you have to figure out how to run that imperative data structure. And so that's where Haskell has this nice thing. You can like take an imperative computation and you can say this imperative computation, like nothing escapes from it. It has like no side effects except for writing in memory and stuff. And so I'll just sort of encapsulate it as this like black hole and I'll pretend it's a pure computation.
Right. You can go back to being pure by delimiting the range of the side effects.
Yeah.
Yeah, okay. Okay.
So
no. It's a thing. I'm not there yet with simple, but I probably get there at some point. I have to sort what am I doing. Right now, I guess I'm entirely imperative with support for functional and support for true finals. So you get the side effect free computational model if you want it. All right. Are we all dead? Is it done? What else? I whined about how hard it was to debug the last 3 stages of simple already. But it's closing in. So at some point, I think chapter 21 lands and we get to move on to something more exciting.
Well, there was the thing I posted last night / this morning.
Yeah.
Winston. So I found a scheduling issue, and then the solution, or at least part of the solution, seemed to be saying if you have an infinite loop, you can't disconnect the memory edge from its sort of like quote unquote output, even though technically it doesn't have an output, because like that loop is still doing things which, are externally observable. And so that external observability is represented also by that memory edge.
Yes, I didn't follow where the bug came from there, because as far as I know, you should still end up with a Phi on the loop header that's at the memory, and then you have a bunch of dependent objects and it rolls back around to the Phi, and nothing should have died there.
Yeah, the thing was that the early schedule picked up the nodes because they're still there, but the late schedule had no path to it, and so it never even looked at the.
But okay,
node.
Right. But now you said they had no path to it, but the late schedule should have followed through the never branch check. He has to reach the body of the infinite loop. That's the whole point of the never branch, is so that he can find it.
Yeah. It followed the never branch, and then there's that control edge,
And then he hits
which
the
is
loop
never
header.
followed. But coming out of that control edge is at the that control edge doesn't get the memory edge attached to it. Maybe it needs to. It doesn't.
The never
And
node should then point to the loop header, which has all the Phis, which will have the memory.
that's the loop headers at before the loop, and the if statement that's doing something is inside the loop, and so it's not.
The loop header is the loop. I mean, so you had the loop node. Sorry, when I say loop header, I meant loop node.
Yeah, but the loop node is the top of the loop.
Right.
So memory stuff was getting scheduled before the loop, but the stuff that was inside the loop was ending up it's there, but it's right in the loop node rather than deeper in the else branch where it belongs. So it was not scheduled correctly because it wasn't being
late
down
didn't visit it.
Late didn't even visit it because it only picked up on the memory edge after it went through the loop node.
I would have said memory should find the loop, find the Phis on the loop, pick up all the Phi inputs, including the back edges, and find the back edges. But I might be wrong. I'd have to go look now.
Right. It should pick up the back edge. Yeah, it didn't though. I don't know. I mean, I traced through it. I definitely didn't see it looking at that.
At one point, I kept memory edges on never nodes on purpose, exactly for this problem. And I yanked them at some point because I thought it was unnecessary or I had some other issue. So maybe the answer is they actually do need to be there. And here's your test case.
Yeah. It's a short test case, and I would think that it could be switched over to something that's simple specific.
Yeah, you store in an infinite loop into an array.
Yeah.
I
made that change to put the sort of marker interface for mem store and mem load. I think that's a good thing because I suddenly noticed anti-dependencies showing up on my nodes, which weren't there either.
Well, if you have stores, they don't.
Well, I have loads of nodes like send node is a store, but it's not a store node.
Yes.
It was a PE memory op, which was a mem op node, and none of this stuff inherited from either load node or store node.
Right, but they don't need memory dependencies, anti-dependencies.
They do.
They do. Let me explain why. Oh, you do need them, but they should be on a generic alias class that covers. They should have a specific. In your case, you're cheating on the memory edge. You need to have a different alias class.
Yeah, I need to eventually do proper memory aliasing, and then like sends and receives are all their own alias versus CRAM loads and stores, which are separate, and those weren't getting anti-dependencies either.
C2 would call them an abstract IO, but then I wouldn't do dependencies. I just force serialization all the way down the line. You're not yet like your receives produce memory too, right? So that's the same as abstract IO. It's not really a memory edge. It shouldn't have an anti-dependence. It should have a hard serialized line. Broken up into equivalence classes for the different sockets, but otherwise it's a hard.
That's sort of what the memory edge.
Yeah.
It can't be a hard serialized line because you have like control flow.
No, it's a hard serialized line, and you have control flow still, which needs Phi functions, and schedule late should schedule you late down in the if test branch. You're missing the schedule late. That needs to happen. You don't need the anti-dependencies.
As soon as I brought the memory edge back, then it's scheduled.
So. Right, but that doesn't. But that means potluck as opposed to this is the right answer. The right thing for the right reason here.
Well, I don't know why it didn't come around the back edge. I'll have to look at that.
That's what I would claim. First, understand why it doesn't come around the back edge, and it could be that the algorithm knows it doesn't need to go around the back edge because you get reached from below, except exactly for infinite loops.
The memory chain does go around the loop, like it is there. I looked at it, so. Why the algo didn't go around the back edge?
I mean, I can maybe debug online via just asking questions. What the hell's going on here? This is code gens is like global code motion. This is schedule late. This is breadth
Wanna share?
first.
So the interesting thing is that right after that, so I got that test. It's like that was like a really narrowed down version of the program that I was looking at. I got it apparently correct, and then I said, okay, brought back the bigger version, and now I've got another weird one, which I was just started tracking down because I was in a couple meetings, but um, now the local scheduler made 3 copies of one of my memory nodes. And
Oh,
I'm like, that's confusing. So I was just looking through that right now. I have no,
he only makes copies if he thinks you've inherited from somebody who's clonable.
yeah, no, this is after cloning. So I don't know. I'm figuring
All
it
right.
out.
Yeah. I was looking at the algorithm for schedule late, which just does a breadth first scheduling and then copies the answers. And the breadth first guy says start at the stop and go up and pull things off, and you're all pinned around, and Phis and regions directly get their things, and then look at for your uses and then repeat again, and then that's put more things to work with. So here's the actual, I'm doing a do, but oh, when do I go through a fee? So I would claim you should have walked through the CFG because it went through the tail end of the never branch to the branch to the loop. Um, loop should have walked through again here and come to block head. When did you get the fees? You keep walking out from CFG up, but I don't go backwards from a region to get fees. You could be right. He doesn't do the back edge. He needs to be caught from below. Yeah, I
I mean,
think that's
maybe
what
the
it
solution
is.
is that it should look at the go around the back edge.
If you're doing the schedule late, you come from below. You're walking up from stop towards start, and if you hit the bottom of a loop, what it really means is you hit some uses that have escaped a loop, and then you begin to deal with the uses that are in the body of the loop that are escaping the loop. But you never hit, in this case, infinite loop, you never hit the bottom of the loop, except via the control edge. And then I went to never nodes, and I thought I had memory edges on them at one point, and then got rid of them. Let me see here. This will be in probably in the loop node. Oh, look at that. It's per frame. That's interesting. So somewhere in here, I say never node. And I thought I grabbed a bunch of shit and added it on the end to keep things alive. Here's merging all the different never nodes together.
Yeah, but it specifically sets mem to top for those.
Right. But that is then fed into the never node. So he doesn't track it. And the claim here is he ought to be taking the mem. So the return memory is not what you're looking for. If you just comment this thing out here, I saw your change was like, do this. That's wrong.
Yeah, exactly.
That's wrong because that means that you kept the prior mem. The prior mem is the return mem. Well, if you have a test that's got a bunch of infinite loops that you might fall into one and then stay forever and do something with side effects, that's cool. Or you might exit. Well, you're taking the exit memory, but the exit memory might not be available if you early on took a path over to this infinite loop and stuck in it. You don't want the exit memory directly.
I agree. And, this ties back to something that we hit a while ago, which was, remember, I had switched the orders of some peeps and said, if a peep is, if a fee has one entry or one thing being selected, you can just replace it with a thing being selected. And then but before that I had if a fee's on a dead region, you can just get rid of it entirely. And that was deleting fees, which would then break the connection to the return node sometimes if the control flow went dead early, or if the control flow went dead late, sometimes it would keep the memory edge because you'd get rid of the fee, and then you'd never know that the control that it was tied to went dead.
There was
So,
a requirement to kill
so I
things
had
in
to,
order so that you could track all the things that were dying and make sure they all got taken away.
yeah. So I changed that one back, and things stopped being broken. But it, yeah. Anyway, that's an aside, I guess. So
Um,
what do you so
yeah,
that
the issue I have here is that I've been walking the control flow. I have found the infinite loop. I know I have it. Um, I don't know what flavor of memory in here is the one that makes sense to claim makes it to the exit. So probably the right answer is I should go find the memory that's on the feed. The only thing I have really here is I have a function header called not fun node. I have the this pointer, which is known to be a loop node. And
yeah,
one of the users of the loop node is memory or not. If there's no fee memory on the loop, then there is no live memory being modified in the loop.
yeah,
I
I'm
can find
going
the
to the
memory on the
same
loop.
place. Yeah.
And instead of grabbing some effort to grab at least the memory from the return, when I want to grab the exit memory, instead of top here, I'd be grabbing memory from a fee off of the loop. That was a
Yeah.
memory fee off the loop.
Yeah.
That probably
I,
solves your problem.
I think that's correct. Yeah, I think you're right.
And that's
So
not.
basically, you have to say if the loop has memory, the loop head has a fee which is a memory
Yep.
user, then that mem that gets defined a few lines up there
Yeah.
before the if statement
Yeah.
gets set to that. Otherwise, it gets set to top.
It is right. Well, no, it doesn't matter. If you the return here that you find on this line for mem return, that one you need. You always need the memory return.
Oh, okay.
So if you don't take the infinite loop path, you take the normal exit path. That's the memory for the normal exit path.
All right.
So you need that memory. Okay. If you fall into the loop, you need a loop header memory if there is one.
Right.
And this stanza is just setting up all the merge points from all the never exits in the program to make them all fold into one spot before they hit the return.
Yeah.
Here when I use top, what I really want to say here is take this pointer's fee, memory fee, if it has one. If
Yeah.
it doesn't, I think it's okay to use top. It may be okay to use the return. I don't think you can ever use the return. It'd be top.
Yeah. I think it's yeah.
And so there's something up here that says, fee node, go find it based on memory
I'm gonna
type.
try and make
I have
that
a shortcut
change
if I go
right now.
look for that. I don't know it off the top of my head.
Yeah. I'll see if I can do that change real quick, and I'll see if it works.
Okay, yeah, right. And modify your PR and I'll take a look again.
Yeah.
Yeah, but we need this memory here because that's the one that the return uses if you don't take the infinite path. So that one has to happen.
Yeah.
And then I think you're right. We don't walk the fees on the back edge. The schedule 8 doesn't walk the fees on the back edge going up. It expects to find an entry point into loop. It finds the loop exit values. He's walking up the loop exit values. There's no exit. There's no loop exit values. So he doesn't end up scheduling late. But it's an infinite loop, so schedule 8 doesn't look like it's bad. But in fact, if you have side effects like your send does, you actually do need to schedule 8. So seems legit. Okay.
Okay.
Now I go
And
find
maybe
how
this
to-
is causing my local scheduling bug too. So
Well, what you showed me was not a local. It was the local schedule was a canary in the coal mine.
yeah, no. So
local-
what I originally showed you when I said scheduling, I meant global code motion because in my
Oh.
head that's also scheduling.
I
But,
gotcha.
versus local scheduling.
Right. Okay, gotcha.
So, but now I have a genuine local scheduling issue, which I could show you now, or I can.
We got
Yeah,
time.
why don't I show you? Because I have actually something I can show.
I'm working it on my end. Hang on a second. I had to find the button. Okay. Yeah, try sharing.
Okay, give me a second because I'm just gonna like. Yeah. Okay.
So
There.
for a future audience, these scheduling bugs, all these things, the compiler thing, they all have their, it's algorithm heavy. Take your graph algorithm course in college. It pays off. What's
So
going
here's
on here
the
is not really C of nodes related at all. It's just a global
yeah.
scheduling. Anybody's global scheduling algorithm has to deal with these things.
Yeah. So here's the program. So I didn't try and narrow this program down yet. So there's like a lot of stuff, but I'll show you here. I think it.
You have to put a bigger font on it as well,
Okay.
or
So
you
I'm
want to
gonna.
debug in real time, but this is a video for people to watch and they can't read that.
Yeah. So I have the late schedule and local schedule here. So on the left is a late schedule, on the right is the local schedule, and this is
Twice
the
as big of font minimum.
so so
Yeah, I'd say
so
again,
I'm just
somebody
gonna
else,
walk.
not me, I can read this. Somebody else, not me, says this is good enough. Because I
Is
think
that okay?
people with smaller
Looks pretty
screens
okay.
have more issues.
That's fine.
Yeah. Okay. So
Okay.
let me see if I can find this here. So lots of things get changed when local scheduled, but basically, um, I have this node 34 send.
Mm-hmm.
This is a like effectful node on the memory chain, and it got stuck in here, but also
Yeah.
here,
Let me, oh, I see. Oh, look at that.
here, and here.
Wait,
So
where's the other one? 30. Oh, I see.
yeah,
Okay.
so okay, so that's actually a terrible way of looking at it. I'm gonna get out of this view.
Just go Control S,
Get
search
rid of-
for send 34 space send one, and you'll see 3 copies. That'll be bad. So to read this for people, this is an ASCII dump for C of nodes, C2 simple. The 34 send one would be 30 for node number 34 unique ID. The shall be only one. If you see it 3 times, it meant that it got printed 3 times by the ASM printer, which generally means he found you 3 times in 3 different basic blocks. So
Yeah.
we're at the point of scheduling, so you get basic blocks. It's not really C of nodes anymore. That's
Yeah.
bad. So
Now,
where are you in the scheduling process? You're in local scheduling?
This is after local scheduling, yeah.
Okay.
I was sort of snapshotting this thing after every major step as I was sort of trying to figure out what's
Yeah,
going
okay.
on.
So I would validate that this is, I mean, for debugging purposes, I would validate this is going on by in the debugger, pull up node 11 and look at his output list and see that you see send one twice and or node 34. It's like the ASM printer has its issues. He tries hard to say, if I have a broken graph, I will still print under best effort to go print something. Nonetheless, he could be broken and incorrectly be printing that node 3 times. And more likely there is something broken, and then the ASM printer also gets confused, and you get extra prints on it, and you're like, oh shit, really ugly things are going on. Now, during local schedule, you will see that node 3 times. If you're in the middle of local schedule, you'll see that node 3 times or more.
Yeah. I'm just a handful of steps into local scheduling.
Yeah, that
So
you could see it not in 2 different blocks. It should be in 1 block, but it
yeah.
may appear many times because I don't update the output list. I have a list of things in the output list, and then
Mhm.
I arrange that I can find them all, and then I start adding them in, but I leave the rest of the output list unmodified, untouched. It's just junk at that point. But the ASM printer comes along and says, I'll print the whole thing, and you'll get twice. That happens.
Yeah.
But you shall not get your node ID 24. So he has a send in node ID 24 output list. I see it there.
Yeah.
Now go find node 11. You can just do the find call. Go find node 11. Look at his output list.
Okay.
And then if you're in the middle of local scheduling, we have to go find which local scheduling you're in the middle of, because you're in the middle of 11. He may have find twice if it was in there at least once.
Node 11 is a wait, we
Yeah,
wanted
it's,
node
it should.
11. It's a constant.
No, then you have some breakage between your things, because he said the print you were showing me claimed you had a control flow graph, node 11, right there. 11
Right.
L11. That's that region.
Yeah.
Or you have you have broken numbering then. I've seen that happen on your pass before as well, where somewhere you
Could be
got
in 24 here.
He takes an input from.
Yeah. What's
No,
going on?
that's you don't print. If you're
This-
in a certain point in the
this-
printer, he doesn't print the
This
control input. So you have to
Yeah,
go
but
find
anyway, like
11 again. Now have a suspicion that you have node numbers from pre and post instruction selection, and the 11 might be a pre-numbered and the send got truly moved to node 24. But go back and find
maybe, but I doubt it.
go do a find in node 11, and what did you get? Where is the
Here.
result? So he says he's a con node. That is not a region. He's a con 0. Okay, so you have this
Hold
bug.
on, because so 11 is the region after the if block in the loop.
No, that is not correct. That is close, but it's not. 11 is two nodes. One, a constant from pre-instruction selection, and one is the region you're looking at here. You have a punning of type node numbers, and now all bets are off. Something in instruction selection picked up a pre-version of the original 0 node.
Sorry, hold on.
Uh-huh.
I went too far up the chain here, and I was looking at the wrong graph. Okay, hold on.
Okay.
Let me try this again. Stop dot find 11. Here we go. No.
Now,
Wait.
you need to go find your code. You had to go up at least one layer to go find.
BB is a node. Okay, here we go. Region node.
That
Sorry,
looks better.
confusion.
Okay, now look at his output list. Okay, there are no sends in the output list.
No.
Okay, now what? And you're on the current block. That's because you're on this current block you're doing here.
I'm partway through scheduler. I could just let it run through, but or I could start over and
Yeah, I would start over and get through the local scheduler, and let's see if we can find multiple copies of send one floating around. In the middle of the scheduler, you get bogus versions.
Yeah, okay. So we want to stop.
But also, I don't know if this is this interesting to people? Like, should we bother here? Oh, I've done coding, live stream coding before. I thought it was very boring.
Yeah.
I've watched it. Fine. Yeah, all right, carry on. We'll go. I don't have anything else. No one else say anything. We're doing live debugging session.
Okay. Let me see if I can. Okay, so here I am right before local scheduling.
Okay. Find 11 again. Is that find 11 correct up there?
Nope. Just let me
There's no BBs. You can't do it. So code.find.
Yeah, that's okay. I will.
Yeah, don't go. Stop.
I want to step into this.
No. Yes, you can, but I don't want you to go anywhere or do anything until we find node 11, which you can find right now.
All right. So
that's because as soon as the local scheduler starts editing things, it's the wrong, you're looking at the wrong thing.
Yeah, okay, got it.
And now look at his outputs. And he has no send one. Okay, find 24. And look at his outputs. There's your send one. Okay, so I claim that at the moment, the graph is all correct.
Yeah, I believe it is.
And local scheduler only edits one basic block at a time, so he shall not move a send one from one block to another. That's not local. So I don't buy that. So now I'll step over this. Just go to the complete through, finish local scheduling all the way out. And look again, see if we're broken. Yeah, you had another breakpoint, yeah.
Okay, sorry for the confusion. There we go. All right.
Now we go 24. Yep.
24.
Yep. Send in front of the region. That's probably correct.
11.
And fine. 11. No send. Okay, so I have no bugs in local scheduling showing at the moment.
Oh, okay.
So carry on and find your break.
Find my break?
Okay. Well, you got here because you thought there was a bug.
Yeah.
So where is your bug evidence?
Let's do code toString. Let's see what actually we can just view it right here.
Yeah, click that guy. Okay, so I clean, that looks really like a broken ASM printer.
Oh,
No, I see
okay.
your 271s, the broken man, but that would be ugly. That's the two string being ugly.
Hmm. Okay. It's
Go do
coming from the
code.asm. I
ASM as
think you can
well.
do, you might be able to do code.asm now. You said
Yep.
code.toString, try code.asm. It's unclear to me that you can at the moment. No, okay, fine.
Okay.
Um, yeah, I think you hit the two string limit here, and we should probably debug why two string is giving misleading information. If you
Hmm.
carry on from here, though, stop at
Yeah.
after regalloc, where I know you can use the asm dump. Stop after regalloc.
Okay.
Yeah, and now try codasm. And you have some other bug that is not mine. That is probably you have a printer in one of your new print guys that's missing. So you can
That's
go crack open the result there. Look at the stack trace. We can go debug why you can't print.
yeah, okay.
Oh man, sorry, I can't follow. The line numbers are hidden. I don't know what line number you're looking for and stuff.
Yeah. Um, so
Yeah.
null pointer code dot encoding. Oh, I think I need to do one more step because the
Well, encoding will also print, but you should be able to print here, but you have to go ask what node type is failing to go code. That's not the line number you're crashing on, or I can't tell what line number you're crashing on because the stack trace isn't wide enough to print it. Widen the stack
uh,
trace, yeah. This line 67 was the
thousand
last
papers 67 here.
code.encode. Oh, did you set code.encoding? I added that in simple side. If you've mimicked things, you probably didn't add it.
Maybe not. Is this something that just got, well, I haven't
It's
played
fairly
it.
new. Go to codegen.java, not into. Go to codegen.java. You're fairly recent. Go look for under fun here or encoding. It's either cogen or it's encoding, and look for an under fun. Oh, it's probably maybe it's an encoding. I did it so I could get better prints, and then I used it in the printing. Um, yeah, new encoding, and then you said pre-encode and encode. Go find your actual encoding. Somewhere in here, I find a new function. I visit a new function and I record it in a global spot so the ASM printer knows what function he's in, which he
Mhm.
uses to decide how big a stack frame is, which he uses to report offsets into the stack frame.
Hmm. Okay.
So there's a missing line, and since you have an alternative encoder, you probably don't have that line, and I don't know where I put it, and it's a stupid shadow thing. The other one is
Okay.
code.encoding. If fun could be moved probably closer to where you care. It's
Yeah.
essentially it's a backdoor for the printer.
Yeah. I can, for now though, just step forward. I think one more step here. Where was I? Just looking for my thing. Oh, well, one more step here.
Right.
And now I can get the ASM done. So, and it's also producing the multiple. This is why I found it, right? Because
Wow. Okay, so
producing.
there's something broken after boy, but
And
we were stopped right
I'm not
after
sure what
local.
these are. These are new, and I was thinking, those might be anti-dependencies showing up.
Oh, it just says I have a node that didn't get an allocator. I'm giving it allocation.
There shouldn't be a node there. Like
Right, there
there's
shouldn't.
nothing there.
Right. Oh, I see what you're thinking. Um, boy, but now okay, now go find label 11 again. Go code dot find or F whatever of 11.
Yeah. Stop. No
Yeah,
code
you can
because
just say find right there. I have a shortcut for that one. Nah, F.
I don't think so.
Oh, not under. Okay, just the F. No under.
F.
F. Open. Yeah, he's not finding it. Huh. Well, I've had it. Okay. Didn't do the stop one
Sometimes
yet.
it
Code
doesn't
does stop
find
that
it,
fine.
but
I put
yeah.
one on code because
Is
I
there
did
a
it all the
node?
time.
Is there a node here that I can just grab?
Stop. Start.
Yeah,
Just
that's
like
what
you're
I
doing.
thought.
Node dot stop. Yeah.
It
Dot
doesn't.
find.
Oh, You know what? Because this is the CodeGen M2. Ugh,
You don't have a stop in there?
I don't know.
You inherit, so you should. There's your stop. You have one. You got
Well,
it. Just keep
sometimes,
going. Dot find.
sometimes, sometimes IntelliJ just gets really screwy on me, and
Well,
it
I
doesn't.
don't use watches for this either. I use the expression evaluator over there. Yeah, code dot understop dot find. Ignore the red
Yeah,
dot
that finds
find of 11.
11. Okay. Yeah. Huh. Okay.
And look at his output list.
All right.
Okay. So very wildly, no send.
Oh,
And the code
that's
has them
good.
clearly multiple sends.
Yeah. I mean,
Something weird going on here.
yeah. Well, hey,
Go
good.
go find 34. That's your dude. There's more than one 11 or something. Here's your send. Now look at his inputs.
Yeah.
Control proj. So he's pointing at the
Okay.
false. There's nothing to do with the other guy. And then no, yeah, don't go there. Look at the other guy. So he's got a memory. He's got a loop fee for an immediate value. He's got a GemV result. He's got a PE load. Those might 12 and 13 might be your Andy dependencies, but he's not got any. There is no edge between 34 and the loop in either direction, and it's printing in the ASM printer. Well, I
Yeah.
claim an ASM printer bug that I don't understand because the ASM printer says node 11 for all outputs. Well, for outputs does not include node 34.
Yeah.
Hmm. No.
Okay. Well,
Well,
I'll look into the ASM printer. No, it's no problem. It's we don't need to do that here because that's like new thing.
yeah,
But
fine.
yeah, you're right. Okay, I'm glad I asked because I would have been chasing the local scheduler. In fact, I had already started.
Yeah.
So
Okay.
yeah.
This is one of these, you had to trust your tools, but actually the tool's being written on the fly as we go. So the tool has just as many bugs as anything else.
Yeah.
It's super helpful when it works, but I will frequently validate first.
Yeah.
Fine. All right. Well, I think that was a good one. We had a good debugging session on when to go
Yeah,
bug what and
it's a good lesson.
when is
Good
it a tool,
lesson.
right? When is it your tool and when is it the program under toolage?
And when you're working
Check
in
your
a compiler,
assumptions.
it happens all the time.
Mhm.
Validate your sources. That's
Yes.
that's a lesson anybody can use.
And,
Yes.
and the joys of when you're using the debugger and it changes the result. Yeah. We've talked
That
about
one was
before.
very, very hard lesson for me in C2. And I preach about that one. Yes, the debugger shall not. They did in C2 for sure. Shall not
Yeah, you
fix
just
that.
got to collect the techniques to help you avoid those because you're going to trip over something. It's the question is, do you want to trip every 5 minutes or every 5 days, right?
Yeah, well, it's the trip when it's the debugger doing it. The trip it means that you can't find the bug under the debugger, but it happens in production and it happens in testing, and you get it to your desktop and it never repros. That's
I
a
only want to trip when I'm on a soft surface close to the ground. That's basically.
exactly.
Good call.
All right. Excellent. Well, I guess until next week then. All right,
All right.
bye-bye.
Bye.
Bye bye.